So now we are going to discuss the various properties of the fluids. In the last class we had discussed what is a fluid and what does this term includes in fluids. How do we define a fluid? Now we are going to discuss the various properties of the fluids. The first property of a fluid is its density. The second, we have specific gravity, which is nothing but another term to express the density in terms of a reference fluid. Then we have specific weight. The next property is viscosity of a fluid. Then we have surface tension and capillarity. These are some important properties of the fluids, and also the fluids exert pressure, which is a property, most important property of the fluids, and we will discuss also how the pressure is exerted, how the pressure is measured. So first of all, let us discuss its density. The density of a fluid, denoted by this rho symbol, is defined as mass per unit volume. Its unit is kilogram per meter cube or gram per centimeter cube in CGS system. Then we have the specific gravity. Specific gravity is another important term, and this is defined as density of a fluid or a substance which includes all solid, fluid and liquid, solid, liquid and gas, divided by density of a standard substance. Now for solids, the specific gravity, solids and liquids. Specific gravity is given by density of solid or liquid divided by density of water. This is pure water at 4 degrees Celsius. So we compare the density of solid or liquid with density of water at 4 degrees Celsius because water has maximum density at 4 degrees Celsius. For example, if an oil has specific gravity equal to 0.8, it means that density of oil is 0.8 into 1000. This is density of water at 4 degrees Celsius, 1000 kg per meter cube. It is 800 kg per meter cube. So if specific gravity is less than 1, it means that this oil or the other substance, whatever given, is lighter than water. If it is more than 1, this is heavier than water. And for a gas, the specific gravity is defined as density of the gas divided by density of air at normal temperature and pressure conditions. For gas, we compare the density with density of air at NTP, which is generally the density of air at NTP is 1.29 kg per meter cube. This is the specific gravity. Then we have specific weight. The specific weight of a fluid, this is defined as weight per unit of volume. Weight is mass into gravity divided by volume. Mass by volume is density, so it is density into G, rho G. And its unit is Newton per meter cube. This is the specific weight of a fluid. Then we have viscosity, which I discussed in the last class. What is viscosity? Viscosity is nothing but the stickiness of a fluid. The more is the stickiness, more viscous is the fluid. Like we have oil, honey, etc. are sticky, so viscous, and water is less viscous. And just to make you remind of this, the viscosity is defined as, this is dynamic viscosity, the shear stress divided by the velocity gradient or the strain gradient. Then we have the surface tension. So surface tension is nothing but the property of a fluid by virtue of which the fluid tries to make and maintain a film. And this we will be discussing in detail in the next classes also. What is the surface tension? And this is because of the cohesive forces of the fluid molecules. There are two types of forces, cohesive and adhesive. So surface tension is because of cohesion or the cohesive forces. That is the forces which are present among the molecules of the fluid. And capillarity is because of adhesive nature, adhesive forces. The forces which are present among two different substances. And this is regarding molecules of same substance. Capillarity, we know that if I take a fluid in this container and if I have a capillarity, that is a tube, the ratio of diameter to height is very small. Actually, this should be, the diameter should be of the order of the thickness of hair, of our hair. So this acts as capillarity, and the fluid, when this capillary tube or this tube of very small diameter is dipped inside a fluid, then the fluid either rises in the tube or falls. And this rise or fall, which we will be discussing later on in detail, this property is known as capillarity, which is just because of adhesiveness of the, or adhesive nature of the forces, attraction of the molecules of this tube with these fluid molecules. Then we have pressure. Pressure, you know that pressure is nothing but force exerted on a very small area normal to the surface. Suppose this is the surface and fluid is, there is a column of fluid on the surface, then the force exerted on this small area per unit of this area in the direction normal to this is called pressure. So this is force F and this small area is A, F by A. So its unit is Newton per meter square, or also known as Pascal. We can express the pressure in different types. What is atmospheric pressure? How we express the pressure above atmosphere? How we express the pressure below the atmosphere? And that we will be discussing just now. So you can note down these things. So now we are going to discuss the topic of fluid pressure. So we know that the fluids exert pressure and on all the surfaces and of the container in which they are contained, and we have to measure that pressure. First of all, let us study how is the pressure varying with respect to the vertical distance, that is the depth. First of all, you should know the atmospheric pressure. This is the pressure exerted by the atmosphere on any surface, and this is equal to 1.0125 into 10 raised to the power 5 Newton per meter square. The unit of pressure is Newton per meter square, also known as Pascal, and we define another unit which is 1 bar, 10 raised to the power 5 Newton per meter square. This is bar, which is the pressure of 1 bar is used for measuring the atmospheric pressure. Bar means barometer, which is the pressure measuring device for the atmospheric pressure. So, if we have the pressure which is above the atmospheric pressure, so this is the zero pressure line, and this is the atmospheric pressure. The pressure may be above atmospheric and below atmospheric. The pressure above the atmospheric pressure is called gauge pressure. Like you go to the petrol pump, and ask the person to inflate the tires of your vehicle, then the pressure there, the unit of pressure is either kilogram force per centimeter square, etc. Then the pressure there is measured in terms of this gauge pressure. That is, the pressure above the atmospheric is called gauge pressure. From zero pressure to this point, this is the atmospheric pressure, and here the pressure above the atmospheric pressure is called gauge pressure. And the value of pressure with respect to this is called the absolute pressure. So I can write absolute pressure is equal to atmospheric plus gauge pressure. Or gauge pressure is absolute minus atmospheric pressure. If we have pressure below the atmospheric pressure, this is called vacuum pressure. So vacuum is below atmospheric and not negative pressure. And there is a misnomer. Sometimes the students, what they understand is vacuum is negative pressure. No, not negative pressure. This is below the atmospheric pressure. So the absolute pressure with respect to this, as far as this vacuum pressure is concerned, this is the absolute pressure. So this is how we define pressure above atmospheric and below atmospheric pressure. Now, how do we measure the pressure? Suppose this is the surface over which a column of a fluid is standing. This is the column of fluid, maybe water or any other fluid, and this is the free surface. Let the height of this column from this base is h, and suppose this is having the cross section area. Suppose this is having circular cross section or maybe any other cross section. The cross section area is A of the fluid. This is open to atmosphere, so here the pressure is atmospheric pressure. The density of this fluid is rho, its mass is m. So we have to find what is the pressure exerted by the fluid on this surface. So you know that pressure is force exerted on normal to this surface, that is normal to this surface here. F is the force, which is nothing but equal to weight of this column of the fluid divided by the area, normal area normal to this surface, cross section area, weight divided by area. So weight is mg divided by A, mass is density volume into G divided by A, and the ratio of volume to area of cross section is nothing but the height, h rho G. So this is how we write the pressure exerted by the fluid. Pressure is the product of height of the column of the fluid, density of the fluid, and G is the acceleration due to gravity. Suppose I have here this column of water, and water is having a height of hw. This is water column. And we have, suppose, any other fluid like air, which is having the height HA, air column. And you have to find what is the height of air column or what is the height of water column if I measure the pressure using this. So I can write that for the same pressure, P is equal to pressure exerted by the water column HW, density of water G, equal to pressure exerted by air column, and from this you can find the equivalent height of another column if I use some other fluid to measure the pressure. What is the use of this is, you know that when we are using the barometer, we measure the atmospheric pressure using the mercury, and height of 76 centimeter of mercury is equal to 1 atmospheric pressure. What is the meaning of this? The meaning of this is 76 centimeter high column of mercury having any cross section area, suppose unit cross section area 1 centimeter square, if kept on a surface like ground, it will be exerting the pressure on the ground equal to this pressure, the 1 atmospheric pressure. Then there is a question, why do we use mercury in place of, like we can use any other fluid, like we can use oil, air, water, etc. So the answer to this column is, this question is, if I have mercury exerting this length, exerting 1 atmospheric pressure, then this is equal to 76 centimeter, convert this into meter. Density of mercury is 13.6 or 13,600 kilogram per meter cube into G, and for this if I use water, height of water column, density of water is 1000 into G. So you will be getting height of water column, if I use water in place of mercury in barometer, this is equal to 76.76 into 13.6 meters. So it will be 13.6 times longer than the tube which is used for containing the mercury. So it will be a very long value, very long tube to contain the water, and air is having lesser density, so it will be having even higher value of the tube length. That's why we use mercury, because this is a metal which is liquid at room temperature and it is having very high density, so it is used for measuring the pressure in the barometer. So you can note it down. Now we are going to discuss the laws related to fluid pressure and the measurement. We shall also study how is the pressure varying with depth inside a fluid. First is Pascal's law. So this law states, Pascal's law, the hydrostatic law, this states that as we move down inside the fluid pressure is increasing. This is obvious because suppose this is the column of the fluid, say water, and at this point, this is the free surface. The pressure exerted at any point on this surface is because of the atmosphere. Here the pressure is atmospheric pressure. If I move to some other point inside the fluid, then the pressure here is at this surface is atmospheric pressure plus the pressure exerted by the fluid above this line or above this surface. So as we move down, the pressure of the column of the fluid above that surface is increasing. At this point, atmospheric pressure plus the pressure due to this much column of the fluid, and so on. So as we move down, the pressure is increasing. This is what Pascal has stated, and also the hydrostatic law. And also at same level inside a fluid, the pressure in every direction is same. Now let us discuss this column of fluid. If I take a very small element of fluid here, then pressure acting on this element in every direction, the thickness of this element is very small. Let us take an element which may be inclined. I have taken this intentionally as an inclined element. Its thickness is very small, cross section area is very small, so we can show the pressure acting on this surface, normal to the surface, on this surface, normal to this, and all other surfaces normal pressure is shown, and on this surface this is the normal pressure. So if this thickness is very small, so this is dH with very small thickness, then according to this law, the pressure acting on all the surfaces will be same. So I can write that Px, Py, Pz, or in any other direction for a very small fluid element at same depth, the pressure is same. Now, according to Pascal's law, as I have told you, that if I move in downward direction, the pressure is increasing, and if I move in upward direction, the pressure is increasing. Now, there is a paradox. Suppose if I take these containers, these three containers having same fluid filled up to same height. Then the pressure at the depth or at the same depth, the pressure inside these three will remain same. So we can see that the pressure is force per unit of area. So area here is unit area at the base or at any point at the same depth. If I take this depth to be same for all the three, so the pressure will be same irrespective of the shape of these three containers. Now let us discuss this Pascal's law. Suppose I have this fluid column. This is the open or atmospheric surface, and this is the base fixed, and height of this is say h. And we have a small element which is at a distance y from the free surface, and dy is its thickness. Y is the distance from the free surface, dy is the thickness. Now I can show separately what are the forces which are acting on this column and show its equilibrium. This is the fluid column. Why we are measuring in the downward direction. So the forces acting here are force on this surface because of the water above this surface. So the pressure here is P. Area of cross section of this surface is A. So P into A is the force acting on this surface. Its weight is acting in downward direction, and this is pressing the fluid below this. So the fluid will be applying a force as a reaction in the upward direction. Suppose the change in pressure here is, as we know that pressure increases as we move in downward direction, P plus dP is the pressure multiplied by area of cross section. For its equilibrium, net force in y direction must be 0, and you know that net force in x direction is 0 as thickness is very small, so force in horizontal direction is balanced. So I can write net upward force equal to net downward force. P into A plus W equal to P plus Vp into A. W is the weight of the column, M into G, M is the mass, volume into density. Area of cross section multiplied by dy, this is the volume G. So this becomes or we can write that rho G dy equal to dP. So dP is the change in pressure as we move in the downward direction. So I can write that total change in pressure, rho and G, if I assume constant, density of the fluid is constant. If this is incompressible fluid, ideal fluid, G is also constant, dV. So pressure here on this surface is atmospheric pressure, and pressure here on this surface is pressure due to this column of the liquid. If I move in downward direction, so Y I have measured in this direction, pressure also I have measured in this direction. So from this equation we can find the change in pressure. So from this equation I can write the rate of change of pressure with depth is equal to rho into G, which is nothing but the specific weight of the fluid. So as we move in the downward direction, the pressure is increasing with respect to Y. You may also find in the book dP by dy equal to minus rho G, because in that case Y is measured in upward direction and P is increasing in downward direction. So that's why dP by dy you will find this as minus rho. Here we have taken Y in downward direction, P is also increasing with Y, so dP by dy is positive. So at the free surface I can write the pressure at Y equal to 0 equal to atmospheric pressure, and at the depth pressure at Y equal to H is atmospheric pressure plus rho G into H. So this is how we measure the pressure with the help of Pascal's law. And now after this we will be discussing what are the different devices like manometers to measure the pressure.